Good morning. Today, class, we'll be looking at the forces that act on an object that is sitting on an inclined plane. First, let's take a look at an object at rest sitting on an inclined plane. First thing we want to do is create a free body diagram. So, first force we can always know is always acting on an object is the force due to gravity, and that's going to be straight down. Then we also have the normal force. Now, pay attention here. The normal force, as we've talked before, is a pushing force from a supporting object, a stable object. But the direction is always perpendicular to the contact of the surfaces. So, in this case, we're talking about perpendicular to the inclined plane is the direction of the normal force. It's not straight up opposing gravity directly. It's perpendicular to the surface of the plane. And then we have the force of friction. In this case, because the object is at rest, we're talking about static friction. And the static friction is what's keeping it from sliding down the plane. And remember that friction is always going to impose either the actual motion or the intended motion. And this static friction has a maximum value, which is mu times the normal force, the coefficient of static friction times the normal force. At this point, we've actually labeled all the actual forces that are acting on this object here. But this is where the transition is going to occur for an inclined plane problems. We can no longer think of our normal up and down frame of reference because we have the inclined plane. So we have to decide, do we want to change the normal force and the force of friction that's acting here to be perpendicular and horizontal, perfectly vertical and horizontal, or really what we're going to do is actually break up the force of gravity, and now we're going to start analyzing things in terms of being parallel or perpendicular to the plane of the incline. So the force of gravity needs to be broken up into a parallel and perpendicular component, and as doing such, this is where our trigonometry is going to come into play. Now, when you're breaking up that force of gravity, you have to be careful about understanding what the angle is in reference to when you're applying your trig functions of SOHCAHTOA. So, oftentimes, you'll be given a reference of an angle for the incline of the plane itself, which you can see here is listed as theta. But if you look at the actual lower portion of the triangle that's being created by the vertical force of gravity, and you can see you have a right angle there, it actually makes a little right triangle. And that opposite angle, opposite of theta, we're going to call that alpha. And just looking at that, it makes a triangle. And now we have an actual right triangle. So we have a 90 degree there where the bottom of the plane meets up with the force of gravity. And so we know then that the other two angles will have to equal 90 because all three of these angles together make 180 degrees. So theta plus alpha are going to have to equal 90 degrees. Well, if you look at the parallel force of gravity and the perpendicular force of gravity, together they make a right angle. And the alpha angle is really the angle between the force of gravity parallel and the force of gravity. That must mean that the other angle, the angle between the force of gravity perpendicular and the force of gravity, must be theta, because together they're complementary angles as we just described and discussed in the triangle that you can see in the bottom portion of the plane. But here you can see this relationship working together as well. So in terms of breaking this up using SOHCAHTOA rules, it's this angle theta here that's going to correlate to the inclined plane angle. And so when we find the force of gravity perpendicular, we see that this is really the adjacent side of the angle theta relative to the force of gravity being the perpendicular, the force of gravity being the hypotenuse. So that means the cosine of theta is going to be equal to the force of gravity perpendicular divided by the force of gravity. And then rearranging and multiplying both sides by the force of gravity, we can find that the force of gravity perpendicular is equal to the force of gravity times the cosine of theta. And therefore, when you look at the force of gravity parallel, that's going to be the opposite side. If we were doing vector addition and we were adding these two components together to sum up to find the actual force of gravity, you can see that it would be opposite of the angle theta that we have here. So in that case, the force of gravity parallel is going to be equal to the force of gravity times the sine of theta. So be careful. This is one of the hardest parts in just reorienting your frame of reference to parallel and perpendicular components. Well, once you've broken everything up into the parallel and perpendicular components, then you're ready to actually go ahead and apply Newton's second law. Instead of summing the forces in the horizontal and the vertical direction, we're going to be summing those forces in the perpendicular and the parallel directions, which again are going to be equal to the mass times the acceleration in each of those correlating directions. So, how do we establish the positive direction? Well, we can no longer just say up is positive and down is negative, and we're starting to make this transition here, as I referenced before, that you want to start to establish the positive direction in the direction that you anticipate the object is going to be accelerating, or the system will be going to accelerate. And so if there's a point where there's an angle which we would expect this block to actually slide down, or the object to slide down the ramp, and so we're going to establish that as the positive direction for the parallel. So the force of gravity parallel, which is down the inclined plane, will be the positive direction. And for the perpendicular reference plane, well, let's just establish the force normal, or up out of the plane, is going to be the positive direction. Again, as long as you're maintaining consistency with the direction that you're establishing, you should be fine. And identifying it on your free body diagram will be helpful as well. Now, we are still have an object at rest here, and so I just want to point out some things about friction. So this force of gravity parallel must be less than or equal to the friction force static maximum. Okay, so as long as that's the case, then the object will not accelerate or move at all on the inclined plane. Well, what happens then if that actually does start to accelerate? Let's take a look at that. So now we have an object that's accelerating down the ramp. All of our force of gravity and summing of the forces of Newton's second law can be broken up into the same components with the exact same way that we were just referencing for an object at rest. The only difference is now is that the force of gravity parallel is greater than the force of friction static maximum. So the parallel component of gravity is such that it's greater than the static maximum friction force, and therefore the object will accelerate in that direction down the inclined plane. Just as a point out, as a reminder, so how do we determine that static friction maximum? Well, it's going to be the coefficient of static friction, mu sub s, times the normal force, right? The coefficient of static friction is going to be based on the materials between the two objects, the inclined plane and the object that is on top of it, and therefore that's how you would determine that. Now, the coefficient of static is always going to be greater than the coefficient of kinetic friction. So at the point where the parallel component of gravity is larger than the static friction maximum, then the object will switch over to kinetic friction because it starts to accelerate, it starts sliding, and now is no longer in static friction but kinetic friction. And so mu sub s, or the static coefficient of friction, will now become the kinetic coefficient of friction for the two objects that are sliding with respect to each other. Let's actually take a look at an example and work our way all the way through and solve for the acceleration. A 241-gram wooden block is placed on an MDF board at an angle of 14.4 degrees above horizontal. The coefficient of kinetic friction between the block and the board is 0.22. Determine the acceleration of the block. Okay, so once you've actually understand and read through the problem, the first thing you want to do is write down all the known values. Okay, so we know the mass of the block was 0.241 kilograms. It was given to us as 241 grams, but I went ahead and just converted it to kilograms here because I know I'm going to need to use it in kilograms. So be mindful of grams versus kilograms. The angle of incline was 14.4 degrees of the plane, and the coefficient of kinetic friction was 0.22. Once that's established, let's go ahead and create our free body diagram. Again, the force of gravity being straight down. I have the normal force perpendicular and opposing the plane. And I have the force of kinetic friction, which is opposing the block as it accelerates down the plane. Now, just want to pause for a second. These are the three forces that are actually acting on it. So if you're ever asked to draw a free body diagram of the actual forces acting on it, this is how you would draw it. However, for us to go ahead and work through and solve through the problem, I would need to break up this force of gravity into the parallel and perpendicular components, as we previously discussed. So again, the force of gravity in the perpendicular is going to be the force of gravity times the cosine of theta, the angle of incline. And rather than solving for the force of gravity here, I'm exposing you guys here that there's no reason we can't just substitute the variables that make up the force of gravity, which is the mass times the acceleration due to gravity. So the force of gravity perpendicular is actually equal to mg cosine theta. Plugging in for both the mass, the acceleration due to gravity, and the angle, we find that the force of gravity perpendicular is actually 2.288 newtons. Now going ahead and solve for the force gravity parallel, it's the same thing except force gravity sine of theta. Again, substituting force gravity is mass times acceleration due to gravity times the sine of theta. Plugging in, we find that the force gravity parallel is 0.5874 newtons. So now that we've broken up those two different components of gravity, we have the forces that we need to go ahead and start applying Newton's second law. So let's sum the forces in the perpendicular direction, where the force normal is in the positive minus the force of gravity perpendicular is equal to the mass times the acceleration in the perpendicular direction. Well, as you witnessed and can see here, that the block does not accelerate relative to the perpendicular direction of the inclined plane. So therefore the acceleration is 0, and therefore we find that the force normal is equal to the force of gravity in the perpendicular direction, which was 2.288 newtons. Summing the forces in the parallel direction, we find that the force gravity parallel is in the positive minus the force of kinetic friction will equal the mass times the acceleration in the parallel direction. Again, pointing out here that the force of friction kinetic is going to be the coefficient of kinetic times the normal force. Well, we can rearrange Newton's second law here because we're trying to solve for the acceleration in the parallel, where we find the force gravity parallel minus the kinetic friction force divided by mass. And then substituting in for the force of kinetic friction, we find that the acceleration in the parallel is going to be equal to the force of gravity parallel minus the coefficient of kinetic friction times the normal force, all divided by the mass. So plugging in, we find for the force of gravity parallel is 0.5874 newtons minus the coefficient of kinetic friction of 0.22 times the normal force of 2.288, all divided by the mass in kilograms. We find the acceleration of this block down this inclined plane to be 0.349 meters per second squared. Thank you, and I'll see you soon.